Welcome to this explainer. Today, we're decoding the hidden mathematics of choice. We'll be tracing a set of beautifully dense, handwritten notes that reveal exactly how we calculate these staggering, seemingly infinite possibilities of our world. So let's dive right into this. But before we look at the raw formulas, we've got to ask ourselves a fundamental question. How do mathematicians actually manage to calculate vast, almost infinite outcomes just by shifting a few basic constraints? It seems a bit like magic, honestly, but as we'll see in the source notes today, it's actually just rigorous, beautiful logic. To map this all out, we're following 5 clear steps today. 1. Defining permutations. 2. Proving the permutation formula. 3. Permutations with repetitions allowed. 4. The shift to combinations. And finally, 5. Combinations with repeated selections. All right, step 1. Defining permutations. Let's start with our most rigid mathematical scenario, where literally every single detail matters. Now, a crucial term you'll see throughout these source notes is cardinality. I know, it sounds a bit academic, but honestly, it simply serves as our anchor for the number of items we're dealing with at any given time. Think of n as the cardinality of our total available set, and r as the cardinality of the sequence we're actually drawing out of it. Just keep those 2 letters in your back pocket. They're essentially the main characters of our story. Looking at the author's notes, they define our starting point really clearly. Permutations are sequences where we draw a cardinality of R from a set of n. And here's the kicker for these strict rules. Normal permutations do not allow repetitions of the drawn members. Basically, once you pick an item, boom, it's gone from the pool. Moving right along to step 2, proving the permutation formula. So how does the author logically prove the mathematical formula for these strict sequences? Well, the notes introduce something called the multiplicative principle of counting. It's basically the engine of combinatorics. It shows that picking items sequentially simply means multiplying your choices. If you have, say, n options for your first pick, well, you only have n-1 for your second, then n-2, and so on. The notes break this principle down step by step. Step 1 shows sequential reduction, meaning each choice removes an option from the pool. Then, step 2 is where the magic really happens. By using mathematical induction, the author shows we can represent this massive descending multiplication as just n factorial. You know, that exclamation point you see in math. Finally, step 3 is all about trimming that factorial down so it only counts the R items we actually drew, rather than the entire set. Continuing this derivation on to the second page of the notes, we land on the foundational formula. The absolute crucial point here is this final equation. NPR equals n factorial divided by n minus r factorial. The top part represents all possible arrangements of everything, while the bottom part effectively chops off the arrangements of the items we left behind. It's just a beautifully elegant way to count. Which brings us to step 3, permutations with repetitions allowed. Because let's face it, the real world isn't always that rigid. What happens when we release our first constraint and allow some elements to be repeated? The author notes that if a permutated sequence has a subsequence of k objects that is permitted to repeat, well, the math has to adapt. Imagine having 2 identical red marbles in a row. If you swap them, you wouldn't even know, right? The sequence looks exactly the same to us. Our previous formula would count that as 2 different sequences, which is obviously incorrect now. To fix this overcounting, we literally just divide out the duplicates. This means throwing k factorial into the bottom of our equation to account for those repeating sequences. It elegantly modifies our original rigid equation by simply sliding that k factorial right into the denominator. The notes even go a step further, showing how to modify it if a very specific subset C is spared from repetition. It really proves just how incredibly flexible these formulas can be. Now for step 4, the shift to combinations. We are now ready to make our biggest conceptual pivot in this whole explainer and release the strict rule of order altogether. This is the great divide in combinatorics. Unlike permutations, where sequence is absolutely everything, think of a highly secure password, where 123 is completely different from 321. The notes define combinations as subsets, where the order of the members does not define uniqueness. Think of tossing a salad. Whether you add tomatoes, then lettuce, or lettuce, then tomatoes, it's still the exact same salad. This represents a huge fundamental shift in our mathematical logic. To figure out the math for this, the author does something incredibly clever. By using the analogy of permutations with limited repetitions that we actually just learned, the author derives the classic combinations formula. Since order no longer matters, we have drastically fewer unique outcomes. We take our permutation formula, but we divide out all the different ways our R chosen items could be arranged. That leaves us with a legendary formula, NCR equals n factorial over R factorial times n minus R factorial. Finally, we arrive at step 5, combinations with repeated selections. All right, here is where things get genuinely wild. Imagine going to an ice cream shop with 10 flavors and you want 3 scoops. Order doesn't matter for your bowl, but you absolutely can choose the same flavor 3 times. The notes describe this as making K selections from N items without regard to order, but where repetitions are fully 100% permitted. To solve this little ice cream dilemma, the author makes a brilliant mathematical leap. They add K minus 1 to the native count of N. Think about it like this. To account for the duplicates we're allowed to draw, we're mathematically expanding the physical size of our starting pool. We literally change our base N to N plus K minus 1. So step 1 is that genius expansion of the cardinality. Step 2 is taking that newly expanded cardinality and plugging it right back into the base combinations formula we learned just a moment ago. And step 3, we arrive at the final grand derivation of this explainer. Yeah, the formula looks pretty complex with all its factorials, but if you've successfully followed the logic up this mathematical mountain, you know it's really just the combinations formula wearing a slightly larger coat to accommodate those repeating choices. Tying all these dense, handwritten pages together reveals just a beautiful map of mathematical logic. As we loosen the constraints, does order matter, are repetitions allowed, the formulas organically grow and adapt. You can see how we start rigid on the top left, and as we change the rules, the equations just seamlessly expand. It is a perfect visual summary of mathematical evolution. So now that you understand how these rules scale from strict sequences to infinite repeating subsets, you really have to ask yourself, where else are these mathematical constraints silently operating in the world around you? Every single time you shuffle a playlist, buy a lottery ticket, or set a new password, you are participating in the exact equations we've unpacked today. The rules of cardinality and sequence are everywhere, quietly calculating the infinite possibilities of your life. Thanks so much for joining me on this explainer, and I hope you never look at a set of choices the exact same way again.